In this video tutorial for Unreal Engine, we're going to take a look at how to make a realistic thin film material that's fast and efficient utilizing HLSL and custom nodes. We'll also take a look at how to create a similar effect utilizing Substrate as well. This is useful to create that iridescent and colorful film reflection like what we see on these soapy bubbles, or similar to what you'd also see in a puddle that has oil, giving us that rainbowy and colorful reflection that changes based on the angle that we're viewing it from. The material we create will have a multitude of controls to adjust the look. We'll be able to define how thick and how thin the film is at different areas, as well as the index of refraction for the film itself, its underlying material, and the air around it. We'll look at a couple different ways of doing our thin film material. If you're using the latest version of Unreal and you go to Edit, Project Settings, and you search for Substrate, you can enable the Substrate Materials beta feature, which will allow us to have much more advanced shading system. And this will support thin film materials. Now, the only problem with that is Substrate can be fairly heavy. So we're also going to take a look at another way we can build our very own thin film material using HLSL with Unreal's custom nodes. And this approach could be used not only in Unreal, but any game engine that is using HLSL or a similar shading language like GLSL. So if we are using Substrate, we can right-click, create a brand new material, and maybe I'll just call it something like M_substrate thin film. And inside that material, in the latest version of Unreal, you're going to see something that looks like a normal material, something that doesn't look very much different than what you're used to. So if you are using Substrate, you're going to have to create a slab. So you create a Substrate slab, and you can connect that to the front material here. And once you do that, this will change, and now this is your material that you start connecting things up to. And to create a thin film effect in Substrate, they have a thin film node that we can create. And we connect up the specular color to the facing angle, the edge specular color to the grazing angle. And then what we can do is set the thickness of the coating, so the thickness of the film. And you can see here that's in micrometers. So 1 means a layer of coating that's 10 micrometers in thickness. And then the IOR is the IOR, or index of refraction of the surface. So as a test, I'm just going to throw in a noise here. I'll preview that noise on here. That's too large of a scale. I'll make it something like this. And since we are dealing with micrometers here, I'm probably going to have to also just make these values a lot smaller. So by doing that, connecting this up and giving it my IOR of the surface, maybe 1.4 or something, we'll then get our kind of thin film coating and our effect of when we change the camera angle, you see those colors changing. So our noise is determining the thickness of that layer, which you can change to any texture that you want. You know, I could change the scale of this and it will update that pattern because it's changing the thickness of the thin film on that surface. So this is one way we can do this with Substrate. But what if we wanted to know how to do this without Substrate, or have more control over this process, or make it more detailed, or more simplified for performance reasons? That's the next thing we're going to take a look at. So we're going to go back without Substrate enabled and take a look at how we can make our very own thin film material using HLSL. So if we're wanting to make our very own thin film shader, we're going to have to understand the steps to do that. There's a few things we're going to have to do. First, we're going to have to calculate the view angle. So that's our camera angle versus the surface normal of the object with the material. And this is going to determine mainly the reflection strength. So it's very similar to the Fresnel effect, which is pretty much where if you're looking at something at a facing angle, it reflects less light than if you're looking at it from a grazing angle. This is what Fresnel does. It gives you stronger reflections at grazing angles. So we're going to have to calculate that so we can determine the brightness of the reflection. We'll also have to have a way of plugging in a thickness map, which will determine the thickness of the thin film at different areas on your model. So that's why I have this texture here, just to use as a sample for once we create our material. But it will determine what areas are thicker, what areas are thinner, which will set the optical path length inside the film. So resulting in different colors depending on the thickness and thinness of that thin film. And once we have that, we have to compute an interference path. So that will be our thickness plus the angle we're looking at, which will determine how the wavelengths constructively or destructively interfere. Do they stack up and create a brighter color, or do they cancel each other out and create a darker area? And after that, we'll have to also handle polarized reflections separately. So there's S and P polarized reflections. S is perpendicular, P is parallel. Reflections at parallel and perpendicular transmit a little bit differently. So we have to calculate those things separately. And if you've ever used a polarized filter for a camera, or have glasses that have polarized reflections, maybe I'll just pull up a quick example here on Wikipedia. So with a polarizing filter in photography, that essentially cancels out the perpendicular reflections, allowing you to kind of remove reflections from your image. So if you have a camera and you're taking pictures of something like water here, if you have a polarized filter, that cancels out perpendicular reflections, allowing you to see through the water more clearly, as you can see here. So that's kind of what we'll have to calculate, the polarized reflections of perpendicular and parallel separately, and at the very end we're going to combine them both to produce the final result. So that's kind of an overview, very roughly, of the steps that we're going to have to do to make this thin film material. Now we will be cheating this effect quite a bit for performance purposes and also just keeping it more simplified. If you do a very complex thin film material, it's going to get very heavy. So to begin, I'm just going to create a brand new material. I'm going to call it something like M_thin film. We're going to open up that new material. I'm going to make a custom node, and I'm going to add some inputs here. So I'm going to go to the details here and start adding some inputs that I know that we're going to need. So I know I'm going to need the UVs, so I'll make an input called UV. I'll add another input for our thickness map, so I'll call it thickness. I'll add another input for our camera vector. I'll add another input for the normals of the surface. I'll add another input so we can determine the thinnest part of the thin film, so I'll call it thick min. And then I'll do the thickest part, thick max. So ways to set the thin areas in our thickness map and the thick areas of our thickness map. So kind of like a range that you'll be able to determine. And then I'm also going to define N medium, which is going to be our refractive index of the surrounding medium. So that would be air, the thing surrounding the material. If it's underwater, you can set it to water. So air is roughly like an IOR of 1.0 or 1.01, depending on altitude and various things. And that means there's little to no distortion of the light when it passes through. Whereas if you were underwater, the IOR is usually like 1.333 repeating, and that's the IOR for water. And that's why when you look through like a cup of water, the light rays are going from air into the glass, into the water, and through that process, those two things, the glass and the water, have a different IOR, which means they slow down or speed up the light as it passes through, and it bends the light and gives us that kind of magnified look. So that's pretty much what our index of refraction is, and we're going to have the ability to adjust that for the air surrounding the thin film, and then we're going to have a control called N film, which is the index of refraction for the film itself. Now that we have this set up, let's start to connect this up. So what I'm going to do here is I'm going to jump over here. I'm going to connect the things that we know are easy to connect just to get it out of the way. So UV coordinates, that's going to be our texture coordinates. So connect that in. Camera vector we could do. We'll connect that up to our camera vector world space. And then normal, we'll connect that up to our pixel normal world space. So there we go. All of our nodes that are easy to populate connected up. And what we can start to do now is start doing our code here. To make this code a bit more easily visible for you, I'm going to type it in Visual Studio Code, but you could type it directly in here, or Notepad, or really any text editor. So I'll go in here, I'll set it to HLSL, and I'm going to start off by defining pi, since we're going to need that in some of our calculations. So 3.14159, I think that's all I remember. Maybe some of you know more spots to it, but I think that'll be good enough. And then what we're going to do is pretty much calculate how we're looking at the surface. So if we're looking at it straight on, maybe we'll have it return a value of 1. And if we have it looking from like a side angle or a grazing angle, we want it to return like a value 0 or something. So what we're going to do is we're going to make a variable here called cos0, and it's going to give us that. It's going to give us pretty much a value where we can determine, are we looking at the surface directly on or from a grazing angle. So we're going to do absolute value of dot, and we're going to normalize our camera vector, and then normalize our normal surface, and there we go. So this is essentially the angle between the camera and the surface, returning a value. Next, we need to be able to load in and utilize our thickness map, so I'm just going to do float thick map. This is going to be our thickness map. Now, since we're going to treat it as a grayscale texture, with the dark values resembling thinner film, brighter values resembling thicker film, what I'm going to do is I'm going to blend between our min thickness and max thickness values that we defined. So I'm going to do a lerp to blend those two, so thick min and thick max. And as a blend between those two values, I'll use this map. So I'll load in our texture that we defined. So I'll do a texture 2D sample. We called our map thickness sampler, and then we'll use UVs. And since we're loading a grayscale texture, I really only need to use one channel of it. So I'll just use a red channel. That way, if we want to pack other data in there at some point, we could. But I just really need to read one channel. You could read all three, but then you have to divide it by 3, so it's not like stacking and giving us like a weird result. So maybe it's safer just to read one of the channels. Now, earlier I talked about how we're going to have to calculate how much it reflects at the facing angle and grazing angle. This will change depending on the IOR, or index of refraction, of the surface. So we have to calculate how reflective the surface is when viewed at a straight, on angle, or a grazing angle, depending on the refractive index. So to do this, we're going to use a bit of a Fresnel reflectance formula, and it's fairly simple. So I'm going to call this F0, facing angle, and it's going to be pretty much, we're going to use the power, or POW, and we're going to take the IOR of our film minus the IOR of the medium around it, like the air, and we're going to divide that by, again, IOR of the film plus the medium around it to the power of 2. So that's that formula there to pretty much calculate our facing angle reflection. And next we'll get our full Fresnel reflection. So I'll make another variable called Fresnel, and this will utilize our facing angle, but it will also calculate the grazing angle and give us our full angle dependent reflection. So essentially this formula here is going to be like a Schlick approximation formula, and it's a cheap way of calculating Fresnel reflections. So we do our F0 plus 1 minus F0 multiplied by power of 1 minus cos 0 to the power of 5. Now, why to the power of 5 here? And that's really just the power of the Schlick approximation formula. It's the approximation amount, pretty much. It's what they found gave it a pretty good result when compared to real-world materials and doing a full Fresnel equation. So maybe some of you who are a bit more math-heavy might have a better answer, but from my understanding, it's really just the value that they found that roughly approximates a real-world material result with less computation. So that's why the Schlick approximation is a cheap way of doing Fresnel calculations. It's not the most accurate way. Now, the next thing we have to do is define our wavelengths. So when doing these calculations, we're going to have to use wavelengths. And we have to kind of approximate this. So on the computer, we have red, green, and blue pixels. We don't use wavelengths like the real world. The real world, light hits surfaces, it gets absorbed, it bounces off or reflects based on that surface wavelength. So we don't really have that in CG, so we kind of can approximate it and cheat it, but we're going to need it for these calculations. So I'm going to define this variable called lambda, and it's pretty much just going to be a float 3, and we're going to store the wavelengths roughly or approximately for red, green, and blue. So the wavelength for red is roughly about 650, green is 510, and blue is about 475. So we could just do something like that. This is in nanometers. Like the wavelength for red, if you look at like a chart of the whole visible light spectrum, red is roughly around 650 nanometers, green 510, blue 475. So that should be fine for our purposes. Now, finally, let's calculate our reflection color. We have everything we need here to do our full calculations. So I'm going to do float 3, reflection color, yeah, keep it a bit shorter. We'll take our Fresnel, 0.5 plus 0.5 times cosine. So I'll type this out and then maybe we'll go over it. So lambda, and then 2, our film IOR, our thickness map, and then cos 0. And I think that's about it. And we can, at the very end, return that result. So this is our approximated version, our very simple and somewhat fast version of our thin film shader. So this line does most of the magic. It's going to give us that rainbowy reflection that we want. And we start off here with the Fresnel. So that's pretty much going to be how much reflection based on the viewing angle. And then what we do over here, like where the cosine is this is essentially going to create us our oscillating kind of color pattern, or the interference. It's going to pretty much be able to give us those different colors based on whether the waves of the reflections are lining up and being constructive interference or destructive interference and canceling each other out. So why do we have this 0.5 plus 0.5 times? This is remapping that cosine range. Normally it's going to output a range from like -1 to 1. We don't want that. We want it in a range of 0 to 1. So this is really just remapping it to a 0 to 1 range. And again, our lambda here is just our wavelength for our red, green, and blue. Now the right side of this here, where we have our film and our thickness map and cosine 0, this is also part of that same kind of equation here. Like all this is calculating our resulting color. And this part particularly is calculating our phase shift based on the film thickness and the view angle. So when putting this all together, we get our kind of colors that change based on the angle we're viewing from and based on the thickness of the film at that area. So let's go try this out to see if we actually did something that works here, if I've made some critical error mistake. So I'm going to go back into Unreal. I'll paste that in here to our custom node. I'm going to give us a little bit more room here. I'll connect this up for now to our base color. Now this is not ideal. This is not what you probably want for a thin film material that's super accurate. If you want a really accurate thin film shader, you essentially have to restructure, rewrite the whole base material here. But again, we want to keep this performance friendly. We want to not overcomplicate things. So it's a little bit of a cheat at the end of the day. I'm going to make the roughness 0 so we get like very sharp highlights. Specular you can leave at 0.5, 1 if you want to push it a little bit stronger reflections. I'll put it to 1. And now we get some errors here because we need to populate these values. So thickness, I need to plug in my thickness map. So I'll take our text here. I can't plug it in. Well, technically, it seems to let me plug it in, but usually you want to convert it to a texture object before plugging it in here for it to work. Otherwise, it's going to give you an error. So I'll do that. Our IOR for the medium, the air around the surface, and our IOR for the film itself. So for those values, it's really up to you. It's, art directable to what you think looks good. But technically, for maybe some oil puddle or something, maybe I can set the thin film to 200 for the minimum, and maybe something like 500 or so for maximum. And then the IOR for the medium, the air around us, I'm just going to leave that to 1. So there's little to no distortion. And for the film itself, I'll set the IOR to something like maybe 1.5. And now we see our result here. So you see that ball and you see that color that changes based on the viewing angle. Maybe if I view it on a plane, there we go. So look at that. Pretty cool. Now actually looking at this, it does feel a bit brighter than what it should be to me. So, checking through my code here, I'm just going to go back to Visual Studio Code. I actually realize I have a bit of a typo here because it's looking way too bright. This should be Fresnel multiplied, not plus, multiplied. And that will correct that. I was adding them together, and that's going to be a problem. So this should be multiply. A little bit of a typo there. So always check your code over. Let's take that code, let's throw it back in here and update it. That's going to look more like what I expect. Same effect, but just more proper reflection intensity now. So that's pretty cool. We got our thin film, oily kind of effect now. Now, what about those other steps I mentioned? Calculating the perpendicular and parallel reflections separately and adding them together. Well, that's going to be more needed for a more advanced way of calculating the thin film. This material looks pretty good in theory here, but there are some problems with it. If I view it on a flat surface and we go look at it at a very grazing angle, you'll notice that these puddles or these details here that we see, they just start to lose their rainbow color as we go from a very grazing angle. And that technically shouldn't happen. We should retain some of those rings of color. So that's a side effect of our cheap approximate calculations here. So it's not perfect, but we can make it closer to a more realistic result by doing more complex calculations. So if we were to do a more heavier version of this thin film shader, then we could have something that resembles a closer match to real life. So by doing a more complex version of the shader, we can end up with something like this, where when you go to those really grazing angles, it retains the ring of colors more and gives us a more accurate resemblance of what it should do. So there is a more complex way to do this. If you want to see the steps to do that, take a look down the description below. Join the Patreon. You'll get access to a PDF that goes over what we covered in this video and those extra steps to make the more complex material as well. And if you've made the material that you see in this video, don't forget to go into your material and convert things to parameters. By doing that, you can then instance the material and change these settings in real time and see it update. So if I just quickly do that for all these, what you're going to notice I'll be able to do then is change these settings and view the results. I right click and instance it, open it up. Here it is. Here's our controls. And very easily we can change these settings and see everything update on the fly. So much more fun to dial in your settings this way. If you enjoyed this video or you learned something new, don't forget to like and subscribe. And as I mentioned before, down in the description below, you'll find a link to the Patreon. If you are part of the Patreon, you will get access to the PDF for this video, which goes over all the steps we went over in a bit more detail, plus the way to calculate the more complex thin film material. And what about the start of this video where I had those bubbles floating around? How do you get that jiggly movement to it? If you want to see how you can deform your meshes using HLSL and some of these custom nodes, this video here will give you a great walkthrough on how to do that. That's also down in the description below, and you can view that and learn a little bit about how you can start deforming your surfaces with some other approaches using those custom nodes.